Hey everyone! Today, we're going to pull back the curtain on a really powerful tool from Precalculus, Partial Fraction Decomposition. Now, I know the name sounds a little intimidating, but trust me, it's just a super clever way of taking a big, messy fraction and breaking it down into smaller, bite-sized pieces that are way easier to work with.
So here's our game plan. We're going to start by understanding the main idea, what I call the reverse problem. Then, we'll roll up our sleeves and walk through an example step by step. After that, I'm going to show you an awesome shortcut that'll make you feel like a genius. We'll also cover a major trap you've got to watch out for. And then, we'll see the big payoff, why this skill is an absolute game changer for calculus.
Think about it like this. You know how to add 1/2 and 1/3 to get 5/6, right? That's the easy part. But what if I gave you 5/6 and asked you, what two fractions did I add together to get this? That's the challenge. And that's exactly what partial fraction decomposition is. It's the art of unadding a fraction to find its original, simple ingredients.
And that brings us to our first big idea, looking at this as a reverse problem. Now, this isn't just some random algebra exercise to keep you busy. Seriously, getting this down now is going to be absolutely essential for you later on. It's one of those skills that unlocks much harder problems down the road, especially in calculus.
So, here's our mission. We start with a complicated-looking fraction, and our goal is to figure out how to split it into a sum of simpler ones. The whole puzzle is just finding the right numbers for a and b that make this equation hold true.
All right, enough talk. Theory is one thing, but seeing it work is another. So let's jump right into our first example, and I'll walk you through the basic method step by step. No magic, just logic.
Okay, here's our fraction. At first glance, it looks like a bit of a handful, doesn't it? But you're about to see just how neatly we can take this thing apart. First things first, we write down the form we're trying to find, with our unknown constants, a and b, sitting on top of the factors from the original denominator. Then, to make our lives a whole lot easier, we multiply everything by that common denominator. And just like that, all the fractions disappear, leaving us with this much friendlier equation to work with.
Now here comes the really clever part. We need to find a, right? Well, take a look at the term with b in it. It's being multiplied by x plus 1. So what if we just chose x to be -1? That would make the entire b term vanish into thin air. So we plug in x equals -1, do a little bit of quick math, and boom! We know that a has to be 2.
And we can pull the exact same trick to find b. To make the a term disappear, we just need to make x plus 2 equal to 0. So we let x equal -2. Plug it in, run the numbers, and we find out that b is 3. See how elegant that is? We just isolate one variable at a time.
And there it is! We did it! That messy fraction we started with is actually just 2 over x plus 1 plus 3 over x plus 2. We have successfully taken it apart.
Okay, so that method works perfectly. It's solid. But what if I told you there's a way to do all of that in your head in just a few seconds? Well, there is. Let's look at what's called the heavy-side cover-up method. This is a real pro move.
The answer to that is a huge, resounding yes. Once you see the logic behind what we just did, you can use this shortcut to just write down the answer. It's fantastic.
The method itself is almost laughably simple. To find the number on top of a factor, you literally just cover up that factor in the original fraction. Then you plug the root of that factor into everything that's left. That's it. You just do that for each piece.
So let's put this new shortcut to the test on a slightly beefier problem. This one has 3 factors in the denominator, which is where this cover-up method really starts to save you a ton of time. Okay, watch how fast this goes. To get a, we cover the x in the denominator and plug in its root, which is 0. That gives us -1/2. Done. For b, cover the x minus 1 and plug in its root, which is 1. We get 4/3. And for c, we cover x plus 2 and plug in its root, -2. We get 1/6. No big algebraic mess, just lightning-fast substitutions. Now, before you run off and use this for everything, there is one really important catch, a condition that has to be met. All of this only works if our fraction is what we call proper. If it's improper, we have to do an extra step first, and you can't forget it.
And I mean this. This is a huge warning sign. Before you start any of this, you must look at the degrees of the polynomials on the top and bottom. This is easily the #1 mistake people make with these problems.
So what does improper mean here? It's simple. A fraction is improper if the highest power of x on the top is bigger than or even equal to the highest power on the bottom. If you see that, you have to hit the brakes.
You cannot just jump into decomposition. Check out this example. The degree on top is 2, and on the bottom it's also 2. Since they're equal, it's improper. Your first move has to be polynomial long division. When we do that, we get a whole number part, in this case 1, and a new proper fraction that's left over. Now you can take that remainder fraction and decompose it using the methods we just learned.
Phew, okay, we've covered a lot of ground. So let's take a second to recap the biggest traps you need to avoid, and then we'll finally get to the real reason why this whole skill is so incredibly useful.
So here are the 3 big ones. First, like we just said, always check for improper fractions and do the long division first. Second, when you're plugging in negative numbers, be super careful with your signs. It's such an easy place to make a simple mistake. And third, make sure your denominator is factored as much as it possibly can be before you even begin.
After all that algebra, you might be wondering, okay, that's a neat trick, but what's the point? Why did we just spend all this time learning how to break fractions apart?
This right here is the whole reason. In calculus, you'll learn about something called integration, and trying to integrate that original complicated fraction is a nightmare. It's incredibly hard. But integrating the simple little pieces we found, that's one of the easiest things you can do. So partial fraction decomposition is the key that unlocks the problem. It turns one impossible task into several simple ones.
You know, this whole technique is really a lesson in problem solving. It's about taking something that looks overwhelming and breaking it down into manageable parts. So I'll leave you with this thought. What other seemingly impossible problems in math, or even in life, could become simple if you just found the right way to break them down into smaller pieces?